Okay, so before we get started with our material here for Unit 3, want to just make a couple of comments on Test 2. Oops, there we go. So Test 2, probably the most common error made on Test 2 was questions that had multiple answers. If you have a question where you lost points, but it was less than 5 points, chances are if you had a -2 or a -3 on a question, that was because you had one correct answer or had a correct answer, but there are more answers. So when you're doing the corrections on that, make sure you look for those other multiple answers. I believe number 1 had 3 correct answers, number 3 had 2 correct answers. There was another one down there that had 4 correct answers for it. The one with 4, they were all just variations of the same numbers, positives and negatives, but it still came out to 4 correct answers. On your corrections, since I did not specifically say in the directions that there might be some with multiple answers, when you do your corrections on those, if you get them all worked out without my assistance, I will give you back 2/3 of your points on those questions instead of just half points. So just to make that fair. Okay, so anybody have any questions off the test? Okay. And remember, if you're having problems seeing what ones I marked wrong or the grading on the test, all of you should have it back. You should have sent it back to you yesterday, if not Monday afternoon yet. So if you can't see the grading on it, try to open it on a WITC computer. You should be able to see the inking there. If not, let me know. I will save it as a PDF and send it to you that way so you can see what is marked wrong on them. So today we are starting Unit 3. To start Unit 3, we have a little bit of business to finish up from systems of equations yet and matrices. Now I'm going to do that quickly here at the beginning, and then we're going to move on to the next major topic, which is conic sections. But we've been talking about matrices, and we looked at inverses and matrix operations and all that. But what we want to look at today is we want to look at something called a determinant. And a determinant is a property of special types of matrices. By special types, I mean square matrices. So a square matrix is just any matrix where the number of rows equals the number of columns. We're going to specifically work today with 2x2 and 3x3 matrices. As you get larger than 3x3, the method for finding the determinant gets to be a little bit more complex. And I don't want to take the time to get into that here. So let's start out with a 2x2 matrix. So there is a 2x2 matrix. That is a square matrix. Now there's a symbol out there that instructs us to find the determinant. Instead of having the squared off brackets, if we just have straight lines, straight brackets like this, looks almost like an absolute value sign. That is telling us to find the determinant of that matrix. For a 2x2 matrix, we have a down diagonal product That is found by starting at the top left and going down diagonally like that and multiplying those numbers together. 4 times negative 5, is a negative 20. Negative 20 is the down diagonal product. Then we also have an up diagonal product. That is found by starting in the lower left and going up and to the right and multiplying those numbers. So that's 3 times 8, which gives us 24 as our up diagonal product. Our determinant is found by taking the down diagonal product minus the up diagonal product. So in this case, that's a negative 20 minus 24. This matrix has a determinant of a negative 44. Let's do one more example of that. So I'm going to use the straight brackets just to signify the determinant here. So here's our matrix, 3, 0, negative 5, 2. We're going to do the down diagonal product, which is 3 times 2 here. That's a 6. Then we'll do the up diagonal product, which is negative 5 times 0. That's just 0. So our determinant, the down diagonal product of 6 minus the up diagonal product of 0, well, 6 minus 0 is just 6. So that determinant is just 6. I'm going to have you guys try one in your notes. So find this determinant of 5, 4, negative 2, 3. I'll give you about 30 seconds or so, then we'll go over it. So our down diagonal product is 5 times 3 is 15. Our up diagonal, negative 2 times 4 is a negative 8. So we subtract. Down of 15 minus the up of negative 8 gives us a determinant of 23. So the 2 by 2 matrices are pretty simple. When we get to a 3 by 3 matrix, this process gets to be a little more complex. Again, I'm just going to use the straight brackets to indicate that we are doing a determinant. But here, if we just did one down diagonal and one up diagonal, you notice we miss almost half of the numbers in the matrix. The determinant has to summarize all of the numbers in that matrix. So that isn't adequate to just do a single down diagonal and a single up diagonal. So what we do, the down diagonals, there is a down diagonal for every entry in the top row. So we start with the first entry of the top row and we do a down diagonal. That would be 4 times negative 2 times 1, which makes negative 8. The second entry of the top row is the 2. So we do a down diagonal, 2 times 3. Now, we've gone off the side of the matrix. What we do is we wrap around and we pick up this first number at the bottom of the first column there. Well, that's a little tricky. So to avoid confusion, it helps us out if I rewrite that first column 4, 1, 3. So instead of having to wrap around, I can just continue that down diagonal down like this. 2 times 3 times 3 is 18. It's a positive 18, so I'm going to put a plus in front of it. Now the down diagonal for the third entry is going to do the third same type of thing. So I'm going to rewrite the second row again over here. So you can see what I've done is I've rewritten the first row is written there, or the first column I should say is written there again. And the second column is written there so that I don't have to wrap around. I can just go down the diagonals. So this third down diagonal starts with the third entry of that top row. I go 3 times 1 times 4, which is a positive 12. So my down diagonal total is found by adding those up. Negative 8 plus 18 is 10, plus 12 is 22. That's my down diagonal total. Now my up diagonal works the same way, only there's an up diagonal for every entry in the bottom row. So we start with the 3 here. We go 3 times negative 2 times 3. That's a negative 18. The next up diagonal is from the second entry of the bottom row. 4 times 3 times 4. That's a positive 48. The final up diagonal is from the last entry of the bottom row. 1 times 1 times 2 is 2. And we have an up diagonal total. We just add those up. Negative 18 plus 48 is 30, plus 2 is 32. 32 is our up diagonal total. So our determinant, once again, is the down minus the up. So our down total is 22 minus the up total of 32, which gives us a determinant of a negative 10. What we just did here is what's referred to as the diagonal method of finding the determinant for a 3x3 matrix. So let's do another example of that. So I'll give you the matrix here. And we're finding its determinant. Now, to start off with, I'm going to just right away rewrite the first column. So the first column is 5, 2, 3. And I'm also going to rewrite the second column over here. 3, negative 1, 2. So all that does is allows it when I do those up and down diagonals, I don't have to wrap around and whatever. I don't have to find what entry finishes off that diagonal. So going down, I have 5 times negative 1 times 1 is a negative 5. Next I have 3 times 4 times 3 is a positive 36. Finally I have 2 times 2 times 2, which is a positive 8. So that gives me a down diagonal total. Negative 5 plus 36 is 31, plus 8 is 39. So now I have my up diagonals. So going up, I have 3 times negative 1 times 2 is a negative 6. I have 2 times 4 times 5, that's a positive 40. And I have 1 times 2 times 3 is a positive 6. Those add up to 40 for my up diagonal total. So the determinant here is 39, my down, minus my up of 40, a determinant of negative 1. I'm going to have you guys try one. So 7, 2, 3, 0, 4, negative 2, 3, negative 1, 0. Find that determinant. I'll give you a minute, and then we'll go over it. So as you can see, I've already rewritten the first two columns here. So let's do the down diagonals. Now, any diagonal that has a 0 in it is simple to do because when you're multiplying by a 0, it's going to end up being 0. So 7 times 4 times 0 is 0. 2 times negative 2 times 4 is a negative 12. And the third down diagonal also has a 0 in it, so that's a 0. So this adds up to a down diagonal total of negative 12. Going up, 3 times 4 times 3 is a 36. Negative 1 times negative 2 times 7 is a positive 14. And this third one has a 0 in it, actually has two zeros in it, so that's 0. 36 plus 14 plus 0 gives that an up total of 50. So here we have a negative 12 minus 50. That is a determinant of a negative 62. Anybody have any questions there? I'm in class. So there's another way of doing determinants on a 3x3 matrix. If we get time, I'll circle around and I'll come back and look at that later. But I want to make sure we get to the main point of doing determinants, and that is Cramer's rule. Cramer's rule is a method of solving systems of equations using matrices and determinants. Now, we used augmented matrices and had to solve to get the to get that identity matrix on the left, and then the augmentation told us what the result was for each matrix using the Gaussian elimination with back substitution or the Gaussian-Jordan elimination. Cramer's rule simply uses the determinant of matrices, but it has to use multiple matrices for each system of equations. So let's start out with a two-variable system of equations. So there's our system of equations. 3x minus 2y equals 8. 2x plus y equals 3. Cramer defined multiple matrices. The first matrix Cramer defined was a base matrix. So to define his matrices, Cramer made sure the system was set up in standard form, just like we did for our addition method. We had the x's, we had the y's, equals, and then we had the constants. And in the matrices that Cramer created, he used columns and numbers. The base matrix used the column for the x coefficients and the y coefficients. So the x coefficients are 3 and 2. That's the first column of the matrix. The y coefficients are negative 2 and 1. That's the second column of the matrix. Now you'll notice I don't have the square brackets on them. I have those straight lines, which implies we're going to do a determinant. 3 times 1 is 3. Minus 2 times negative 2 is a negative 4. 3 times negative 4 is 7. So the determinant of that base matrix is 7. That base matrix, by the way, is just labeled as M for matrix. Cramer also created an X matrix. The X matrix was labeled MX, M with a little x by it, subscript X. And in the X matrix, Cramer actually excludes the X column, replaces the X column of variables with the constants, and then the Y's are still the second column. So the constants here are the 8 and the 3, so that becomes our first column, 8 and 3. The Y coefficients are still -2 and 1. Again, you'll notice I've got the straight lines instead of the square bracket, so it's implying we're going to do a determinant. So 8 times 1 is 8, that's the down diagonal, minus the up diagonal, 3 times -2 is -6. 8 minus a -6 is 14. That is the determinant of the X matrix. Well, Cramer also defined a Y matrix. The Y matrix was M with a subscript Y. In the Y matrix, it's the Y column that Cramer replaced with the constants. So the X coefficients are back in the first column. The second column is now the constants. So the X coefficients are 3 and 2 still. The constants are 8 and 3. And you'll notice the straight lines implying the determinant. So I've got 3 times 3 is 9, minus my up diagonal is 2 times 6 is 16. 9 minus 16 is a -7. That's the determinant of our M matrix or our Y matrix. Well, what's all this mess tell us about our system of equations? Well, Cramer determined that in a system of equations, the solution for X was equal to the determinant of the X matrix divided by the determinant of that base matrix. So here the X matrix was 14. The determinant of the base matrix was 7. 14 divided by 7 is 2. So that's saying X equals 2. Cramer also determined, you can probably guess what's coming here, that the value for the Y variable was the determinant of the Y matrix divided by the determinant of the base matrix. So the Y matrix has a determinant of -7. The base matrix has a determinant of 7, of +7. -7 divided by +7 is a -1. So Y has a value of -1. The solution for this system of equations is 2, -1. It's really a slick little tool. And you can see for a 2x2, a 2-variable system with 2 equations, it's really quick to whip out those determinants. So let's take, let's do 2x plus y equals -1. -3x minus 2y also equals -1. So what I'm going to have you do, notice this is already set up with the x's, the y's, equals, and then the constants. So I want you to do, we're just going to start out by setting up the base matrix. That's the matrix M. Set up that matrix quick in your notes and determine its determinant. So the x variables, or the x coefficients, are 2 and negative 3. The y coefficients are 1 and negative 2. To do that determinant, we've got 2 times negative 2 is negative 4, minus negative 3 times 1 is a negative 3. Negative 4 minus a negative 3 is a negative 1. That's the determinant of our base matrix. Any questions on that? Okay. Next, I'll have you set up and find the determinant of the X matrix. Remember, in that matrix, we replace the X coefficients with the constants. So our constants are both negative 1 and negative 1. The Y column is 1 and negative 2. Down diagonal, negative 1 times negative 2 is 2, minus up diagonal, negative 1 times 1 is a negative 1. 2 minus a negative 1 is a 3 for the determinant of the X matrix. So I'm going to have you do the Y matrix, set it up, and find its determinant quick. So in the Y matrix, we have the X coefficients, and then the constants replace the Y coefficients. So the X coefficients are 2, negative 3, and the Y coefficient, or the constants, are still negative 1 and negative 1. So our down diagonal, 2 times negative 1 is negative 2, minus the up diagonal, negative 3 times negative 1 is a positive 3. Negative 2 minus 3 is a negative 5 for the determinant of the Y matrix. So then the values for X, we have 3 as the determinant of the X matrix, over negative 1 is the determinant of the base matrix. That gives us X equals negative 3. For Y, we have negative 5 as the determinant of the Y matrix, divided by negative 1 as the determinant of the base matrix, gives us that Y equals 5. So the solution for this system is negative 3, 5. This method works for 3 variable systems with 3 equations. So let's take this system of equations here. 5x minus y plus 2z equals 5. 2x plus 3y minus 2z equals 7. 3x minus 2y minus z equals 11. So I'm going to define our base matrix. That base matrix M is just going to be, instead of x and y, it's x, y, and z columns now. So the x column is 5, 2, and 3. Y column is negative 1, 3, and negative 2. The z column is 2, negative 2, and negative 1. Now finding the determinant of this is a little more difficult. We have to rewrite our columns. The first column, 5, 2, 3. Second column, negative 1, 3, and negative 2. And we'll do our diagonal products. 5 times 3 times negative 1 is a negative 15. Negative 1, negative 2, 3 is a positive 6. 2 times negative 2 is a negative 8. So that adds up to a negative 17 for my down diagonal total. Going up, we have 3 times 3 times 2 is 18. Negative 2 times 5 is a positive 20. Negative 1 times 2 times negative 1 is a positive 2. That gives us an up diagonal total of 40. So now we have negative 17 is our down, minus 40 is the up, giving us a negative 57 is the determinant of our base matrix. Our X matrix. Once again replaces the X coefficients with the constants. So the constants here are 5, 7, and 11. The Y coefficients, negative 1, 3, negative 2. The Z coefficients, 2, negative 2, and negative 1. And we find its determinant. So I'm going to repeat those first columns again. So the first column, 5, 7, 11. Second column, negative 1, 3, and negative 2. And I have to do my down diagonals. 5 times 3 times negative 1 is a negative 15. Negative 1 times negative 2 times 11 is a positive 22. 2 times 7 times negative 2 is a negative 28. That comes up to a negative 21 for my down diagonal total. My up diagonals. 11 times 3 times 2 is a 66. Negative 2 times 5 is a positive 20. Negative 1 times 7 times negative 1 is a positive 7. 66 plus 20 plus 7 is 93 for my up diagonal total. So our determinant, negative 21 minus 93, is a negative 114. So for the Y matrix, it is now the Y column that gets replaced with the constants. So the X column is back, 5, 2, 3. The Y column is replaced with the constants, so 5, 7, 11. And the Z column, the third column, is still the Z coefficients, 2, negative 1. Of course, we rewrite the first column, 5, 2, 3. And the second column, 5, 7, 11. And we do our diagonals to find our determinants. So the first down diagonal, 5 times 7 times 1 is a negative 35. 5 times negative 2 times 3 is a negative 30. 2 times 11 is a 44, positive 44. So what do we have there? Negative 65 plus 44 is a negative 21, I believe, is our down diagonal total there. So then we start our up diagonals. 3 times 7 times 2 is 42. 11 times negative 2 times 5 is a negative 110. Negative 1 times 2 times 5 is a negative 110. Or sorry, negative 1 times 2 times 5 is a negative 10. We add those up. We'll have negative 120, negative 78 is that up diagonal total. So our determinant, negative 21 minus a negative 78 is a positive 57. Now, since this is a 3-variable system, we have to define one more matrix. That's going to be the Z matrix. And in the Z matrix, we replace the column of Z coefficients with the constants. So our X coefficients are still 5, 2, and 3. The Y coefficients are negative 1, 3, and negative 2. And then the constants, of course, are 5, 7, and 11. And then we proceed to find the determinant of that matrix. So we copy down the first column, 5, 2, 3. Second column, negative 1, 3, negative 2. And we start to do our diagonals. So going down our first diagonal, 5 times 3 times 11 is 165. Next diagonal, negative 1 times 7 times 3 is a negative 21. Next diagonal, 5 times 2 times negative 2 is a negative 20. 165 plus a negative 21 plus a negative 20 is 123. It's my down diagonal total. Sorry, 124, not 123. Going up, we got 3 times 3 times 5 is 45. Negative 2 times 7 times 5 is a negative 70. 11 times 2 times negative 1 is a negative 22. That adds up, I believe, to a negative 47. So our determinant here, 124 minus a negative 47 is 171. So to find the value of x, the determinant of the x matrix was a negative 114. The determinant of our base matrix was a negative 57. So x is negative 114 minus divided by negative 57, which is a positive 2. For our value of y, the determinant of the y matrix was 57. The determinant of the base matrix was a negative 57. Y is negative 1. And for z, the determinant of the z matrix was 171. The determinant of the base matrix was negative 57. 171 divided by negative 57 is a negative 3. So the solution for this system is 2, negative 1, negative 3. Any questions there? For a 2 by 2 matrix, it's a really quick, simple process. For the three variable 3 equation systems, it is a little bit more lengthy. Okay, so we have a few minutes before break here. So I want to try to squeeze in a little bit of that other method of finding a determinant for a 3 by 3 matrix. So first thing I'm going to do is I'm going to put a matrix up here. So I got 2, 5, 1, 0, negative 3, 4, 5, 0, negative 2. Each entry in a matrix has two properties. One property is a cofactor. The cofactor of an element in the matrix is either its value or negative 1 times its value. Well, how do we know which? Well, it's based off of position. Let's pick the 5 here. For the 5 is in row 1 and column 2. I add those two numbers together. 1 plus 2 is a 3. Since that is odd, we do the entry times negative 1. So the cofactor for 5 in this matrix is a negative 5. Let's do the cofactor for, I want to find one that's, let's do this 5 down here. That's going to be confusing. Let's do the negative 2 down here. So for the negative 2, it is in row 3 and column 3. If we add those together, 3 plus 3 equals 6. That's even. So since that's even, it's just the entry. So the cofactor for negative 2 in that matrix is just that value, negative 2. The second thing that each entry has is a minor. A minor is a reduced form of the whole matrix. It is reduced by removing the row and the column of the entry. Well, what does that mean? Well, let's go back and do this for the 5 again up there. For the 5, if I remove its row, this is the row the 5 is in. If I remove its column, there's the column the 5 is in. What is left is the 0, 4, 5, negative 2. That matrix, that 2 by 2 matrix, is the minor for 5. Let's look at the negative 2. If I look at the negative 2 in there, I'm going to erase the green lines here quick. Negative 2 is in that row and that column. That leaves us with 2, 5, 0, negative 3. That is the minor for the negative 2. So we can find the determinant of a matrix by expanding a row or column by using cofactors and minors. The expansion for a single element, for a single entry, is equal to its cofactor times the determinant of its minor. So what that means is if I have a row or a column that has a lot of zeros in it, I should pick that one because its cofactor is going to be 0. So I'm going to pick actually a column to use here. I'm going to pick, let's get back here. I'm going to pick column 1 to use. So I'm going to expand about that column. So I'm going to start with the 2. The 2, so the entry is the 2. The cofactor, it's in row 1, column 1, that adds up to 2. That's even, so the cofactor is just 2 times the determinant of the minor. Well, the minor for that 2, if I cross out the row and the column, I'm left with negative 3, 4, 0, negative 2. So I've got a negative 6 positive 6 minus 0. So that determinant of that minor is a 6. So 2 times 6 is 12. The expansion for the 2 is a 12. The next element in that row is the 0. The cofactor of 0 is 0. Doesn't matter. Positive 0, negative 0 doesn't matter. So I'm not even going to do the entry. The expansion of 0 is always 0, no matter what the rest of the matrix looks like. The expansion for the 5, well, the minor is going to be 5, 1, negative 3, 4. I'm going to write that down right now. The 5 itself is in row 3, column 1, that adds up to 4. That's even. So the cofactor is just the 5. Our determinant here, we've got 20 minus a negative 3. That's 20 minus a negative 3 is 23. 5 times 23 is 115. 12 plus 115 is 127. The determinant of that matrix is 127. I'm never going to force you to use an expansion by minors, but the reason I show it to you, in this class, I'm never going to ask you to find a determinant of something larger than 3 by 3. But it can be used, any matrix more than 3 by 3, you cannot use the diagonal method for finding the determinant. So you have to expand it by minors. The problem with that is it gets pretty ugly, because if you have, let's do a 4 by 4. And you're finding that determinant. Well, I'll pick a I'll pick a row here. I'll pick this row. Well, the -2, the entry for the -2, its cofactor, that's in row 2, column 1, that adds up to 3, so that's odd. So -1 times 2 is a +2 as its cofactor. The problem is it's minor. If I cross out the column and row, 7, 2, 4, -1, 2, 4, 2, 3, -2. Its minor is a 3 by 3 matrix, so I still have to find the determinant of that 3 by 3 matrix. So finding the determinant of matrices that are larger than 3 by 3 is a very lengthy process. I won't do that to you. I've gone a couple minutes over here. It is time for our break, so let's go ahead and take. So for our second half of class, we're going to shift gears a little bit here. We're going to put, for a little while at least, we're going to put systems of equations behind us. You've probably noticed that they keep coming up as ways to solve different applications all the time. We're going to start looking at conic sections. And we have actually already looked at a couple of different forms of conic section. A parabola is one form of conic section. And we had its equation, its standard form of its equation, of course, is x plus y squared equals some number. We've had circles. The standard form of an equation for a circle is x squared plus y squared equals a number. Usually use r squared because that value is the square of the radius of that circle. And we'll still look at each of those a little bit more yet. But we had the adjusted form for the parabola. We could have the x plus y squared, or we could have x squared plus y equals a constant. But we adjusted that form as either y equals, remember, a times x minus h squared plus k, or we could have switched the x and the y in that. For the circle, we had x minus h squared plus y minus k squared equals r squared, where the h and the k again are the center of that circle. We're basically moving the origin, the center of the graph, with those coordinates. Two shapes that are conic, the other two conic sections, because there are 4 total, that we have not looked at yet. One is an ellipse. An ellipse, of course, is just that oval shape. Mathematically, it's actually an elongated circle. And the other is a hyperbola. A hyperbola is kind of like two parabolas facing away from each other, like that. What we're going to focus in on today, focusing in on the properties of and the general equation of, is an ellipse. Each of our conic sections is actually defined by some features. Some have a directrix. A directrix is just a line, kind of like a reference line that we use to locate different points on a conic section. Others have a focus or foci. And again, a focus or a multiple foci is just two focuses. is just a point that is used for reference for locating points on the conic section. And then they have axes. Usually minor and major axes. So on an ellipse, first of all, the definition of an ellipse is the set of all points the sum of whose distance from two set points. Those two set points are the foci of that ellipse, by the way, is constant. So what does that mean? That means if I have 2 points, those are my foci. Now I'm just going to say they're 3 units apart, right? If I go 1 unit over here on this side of the right focus, the distance from the foci, this is 4 units here and 1 unit here. So that's a total distance of 5 total units. Every point on that ellipse is going to be a total of 5 units from those foci. So if I draw in the rest of my ellipse, like that. It's a little egg-shaped, but should be symmetrical in both directions. If I pick a point on the ellipse, let's pick that point there in purple. If I add that distance to that distance, those 2 distances will add up to 5 units. If I pick a point here, those 2 distances should add up to 5 units. So other properties of an ellipse, we'll start off with our standard form of equation. It takes the form of x squared plus y squared equals 1. Now you might notice that looks an awful lot like the standard form of an equation for a circle. And it is. Written in that form, it's a circle. A circle is actually a special form of ellipse where the 2 axes are the same length. So a little bit more general form, or more useful form of the equation for an ellipse looks like this. X squared over a squared plus y squared over b squared equals 1. Notice it's still equal to 1 on the right side. For an ellipse and for hyperbola, it's always going to have to be equal to 1 on that right side. Well, let's look at what these other things in here mean. A is referred to as the horizontal semi-axis. What does that mean? That means half of the axis. So if this is my parabola like this, A is the distance from the center to one side, left or right. For the b squared, b, since the b is with the y, is the vertical semi-axis. So what's that mean? Well, B is from the center up to the top or from the center down to the bottom. So let's look at a very simple graph here. If I have x squared over 4 plus y squared over 9 equals 1. The 4 here is telling me that a equals 2 because 2 squared equals 4. So if I assume the center of this ellipse is at the center of the graph, at the origin, that means I go out 2 units to the right to get to the edge of the ellipse. I go out 2 units to the left to get to the edge of the ellipse. The 9 here is telling us that b equals 3 because 3 squared equals 9. So once again, from the origin, that's saying I go up 3 units to get to the edge of the ellipse, or I go down 3 units to get to the edge of the ellipse. There's my ellipse. Now this ellipse is elongated vertically. The vertical axis is the longer axis, so it can go either way. The longest dimension, the longest axis determines the location of the foci. The foci of this ellipse are going to be on the vertical axis because that's the longer axis. If the horizontal axis is longer, then they would be on the horizontal axis. The distance from the center of the ellipse to the focus is going to be labeled C. In an ellipse, we have what's called Pythagorean relationships between A, B, and C. In an ellipse, it is A squared minus B squared equals C squared. Depending on which is longer, A or B. Now what I have up here, it would be B squared minus A squared equals C squared. So we showed that B squared was 9, minus A squared is 4. 9 minus 4 is 5. So C squared equals 5. By taking the square root, I get that C is the square root of 5. So that means this is at positive square root of 5, negative square root of 5 is the location of C there. So if I have x squared over 16 plus y squared over 9 equals 1. My semi-horizontal axis, A, is 4 units because square root of 16 is 4. So from the origin, I can go 4 to either side for my ends of my ellipse. My vertical semi-axis, B equals 3. Because the square root of 9 is 3. So that means it goes up to positive 3 and negative 3. So there's my ellipse. My focus, my foci. are found by locating or finding the value of C. So since A is the larger one here, A squared minus B squared equals C squared. So 16 minus 9 equals C squared. 16 minus 9, of course, gives us 7 equals C squared. So the square root of 7 equals C. Oops. Square root of 7, not square root of C. So what that's telling us is, now the square root of 7 is between 2 and 3. 2.646 about. So one focus is located over here at the negative square root of 7, comma 0. And the other focus is located over here at the positive square root of 7, comma 0. This point, of course, is at 4, 0. This end over here is at negative 4, 0. This point up here is at 0, positive 3. This point down here is at 0, negative 3. Of course, not all of our ellipses are centered at the origin. Just like with parabolas and circles, we move the center of the ellipse by subtracting or adding to the x and y values. So here is a full-blown equation in graphing form for an ellipse. A here, remember A is always with x, is going to equal 5. The square root of 25 is 5. So that means we've got, oops, got to be careful here before I start locating that stuff. I've got to locate my center first. A is 5, B is going to be 4. Our center is going to be at 2, negative 1. Remember, it's always the coordinate of x is always subtracted from x. The coordinate of y is always subtracted from y. So this is x minus 2, which means that's at 2 for the x coordinate. Y plus 1 really means that the y coordinate's at negative 1. Think of that as y minus a negative 1 to get the y plus 1. So at 2, negative 1, that is the center of our ellipse. So now we can go back and use A and B to find the ends of our ellipse. I'm going to label that center here quick just to have it labeled. So for A, it being 5, I go up 5 units to the right. 1, 2, 3, 4, 5. That's going to be at the point 7, negative 1. Or 5 units to the left. That's going to be the point negative 3, negative 1. For B being 4, I go up 4, 1, 2, 3, 4. That's at the point 2, 3. Or I go down 4, 1, 2, 3, 4. That's at the point 2, negative 5. My ellipse is going to get drawn in there. Something like that. My foci. To find C, A is bigger again, so it'll be A squared minus B squared equals C squared. 25 minus 16 equals C squared. Well, 9 equals c squared. So I square root that to get that 3 equals c. So I go 3 units from the center. 1, 2, 3. That's one focus at -1, -1. The other direction, 1, 2, 3. That's my other focus at 5, -1. So those are the foci for that ellipse. So for this ellipse here, I'm going to run out of little space here. I draw this a little lower. First of all, the center, oops, I got some stuff disappeared on me there. There. The center is going to be at -2, 3. So -2, 3, right there is my center. A equals 5. So from there I go 5 units to the left. That's going to be at -7, 3 for one side of the ellipse. 5 units to the right. That's going to be at +3, 3 for the other side of the ellipse. B, the square root of 169, is 13. So up here 13 units, that's going to be at -2, 16. Down here 13 units, that's going to be at -2, -10. So it's going to be a very long, narrow ellipse. To find my foci, it's going to be B is the larger one, so it'll be B squared minus A squared equals C squared. So 169 minus 25 equals C squared. 169 minus 25 is 144. So as we square root each of those, we get that 12 equals C. So C is up here at -2, 15, and down here at -2, -9. Notice they are above and below the center now because the vertical axis is the longer axis. Now, not all of our equations for ellipses are given in such a nice, neat little package. We might have something like this. Couple of things we notice, of course, is that the x squared and y squared bundles are multiplied by numbers. And also, this is not a 1 over here. That's the most important part, is this over here needs to be a 1. So we're going to make that a 1 by dividing by 144. Which means we have to divide the left side by 144 as well. There are two pieces over here that each have to get divided. One is this piece here. When I divide that, I've got the 36 times the x plus 4 squared over 144. Well, 36 over 144 can be reduced. In fact, both of them can be divided by 36, gives us 1 over 4. So when I divide that out, what I get is the x plus 4 squared over 4. Next is dividing out this piece. I do a similar thing there. 4 over 144 can also be reduced. Dividing by 4 gives me 1 over 36. So that part becomes y plus 3 squared over 36. And on the right side, of course, we have 1. So this means our center is at negative 4, negative 3. A is 2, so we go 2 units in each side horizontally. B is 6, so we go 6 units on each side vertically to make our ellipse. And of course C, B is larger here, so it's going to be B squared minus A squared equals C squared. 36 minus 4 equals C squared. So 32 equals C squared. So it's the square root of 32. Square root of 32 is 5 point... Oops, clear that out. .66 basically. So that means we're going to be somewhere in here and here for our foci. I'm assuming you guys can calculate the coordinates for those. So that was pretty simple. All we had to do there to put that in graphic form was divide by the number on the opposite side of the equation in order to make that into a 1. But it can get a step more difficult yet. Oops. We might have something like 4x squared plus 9y squared minus 32x plus 36y plus 64 equals 0. This is the standard form of a conic section. The x squared, the y squared, the x, the y, the constant, and then 0, or equals 0. I'm going to start by putting the x coefficients together. So the 4x squared and the minus 32x I'm going to put together. Then I'm going to put the y variables and their coefficients together. So I've got a positive 9y squared and a positive 36y. I put those together. The 64, I'm going to move over to the other side of the equation. I'm just going to subtract 64. So I got a negative 64 on the other side. Now I'm just going to simply complete the square. Twice. Once for x and once for y. For x, to make this easier on myself, I'm going to factor out the 4. So it's the 4 is factored out. I'm left with x squared minus 8x inside there. To complete the square, though, I need that to be, I divide this by 2 and I square it, right? Negative 8 divided by 2 is negative 4. Squared is 16. So that's x squared minus 8x plus 16. Would make that a perfect square trinomial inside there. This is where this 4 out front comes into play now. It looks like I added 16, but I really added 16 times 4, which is 64. So I have to add 64 to the right side as well. Now I need to complete the square for the y, and I'm going to start out similarly. I am going to factor out the 9. So I factor out the 9, I've got y squared plus 4y. Also similarly there, to complete the square, I take this, divided by 2 and square it. I need a 4 there. That has to be y squared plus 4y plus 4. Makes that a perfect square trinomial. Now again, it looks like I just added 4 there, but I really added 4 times 9. That's 36. So I have to add 36 on that other side. So what I have right now, on the left side, I have 4 times, this is a perfect square trinomial. That's x minus 4 squared. Plus, this is 9 times, this is again a perfect square trinomial. That's y plus 2 squared. On the right side, I've got negative 64, plus 64 is 0, plus 36 is 36. So on the right side, I have 36. Now this looks just like the equation we worked with a few minutes ago. I need to make this on the right side equal 1. Right now it's 36, so I'm just going to divide by the 36. I divide the whole left side by 36. I'm just going to write it out as dividing each piece individually by 36 on the left side. So now 4 over 36 reduces to 1 over 9. So that's x minus 4 squared over 9. Plus 9 over 36 reduces to 1 over 4. So that's y plus 2 squared over 4 equals, on the other side we have just 1. Well, that was a long process. Let's do another one. So 16x squared plus 25y squared minus 300y plus 500 equals 0. So remember the steps. First, I'm going to group the x's together. I have the 16x squared. There are no other x's to group together there. Then I'm going to group the y's together. I have 25y squared and the minus 300y. I'll group those together. The 500, the constant, I'm going to subtract that from each side to put it on the other side of the equation. So I have negative 500 on the right side. The 16x squared, well, I'm going to write it as 16 outside the parentheses with the x squared inside. There's nothing to do there to complete the square. That's already x squared is a perfect square. Since there is no just x term, x squared is already a perfect square. For the y's, I'm going to start by factoring out the 25. So it leaves me y squared because the 25 divides out. Negative 300 divided by 25 is a negative 12. So that's a negative 12y there. I can create a perfect square trinomial with the y's, since I have a linear y term there. Negative 12 divided by 2 is a negative 6. Negative 6 squared is 36. So I need to add 36 to this. So it's y squared minus 12y plus 36. Now, it might look like I've only added 36 there. But what I've really added is 36 times 25. 36 times 25 is, of course, 900. So I added 900 here. Which means on the right side I have negative 500 plus 900 is a positive 400. And now I have to reduce that down on the right side to a 0. So I'm going to divide by 400. I divide the x piece on the left side by 400, and I divide the y piece by 400. Now, 16 and 400 reduce to 1 over 25. The x squared, nothing to do with that. For the y's, 25 and 400, 25 over 400 reduces to 1 over 16. This perfect square trinomial is going to be written as y minus 6 squared. Equals, on the right side, 400 divided by 400 is 1. So there is our graphing form of the equation of that ellipse. I'm going to have you guys try one on your own. I'll give you about 3 or 4 minutes to work on this. 4x squared plus 25y squared minus 24x plus 100y plus 36 equals 0. So I'll give you, like I said, 3 or 4 minutes, and then we'll come back and go. Let's take a look and see how this is going. So we're going to put the x's together. So we got the 4x squared and the negative 24x. I'm going to put those together. We've got the 25y squared and the 100y. We'll put those together. And we're going to subtract 36 from both sides to put negative 36 on the other side. Now for the x, I'm going to factor out the 4, leaving us with x squared minus 6x. For the y, I'm going to factor out the 25, giving me y squared plus 4y. For x, well, negative 6 divided by 2 is negative 3. Squared is 9. So this needs to be x squared minus 6x plus 9. So I added 9 times 4 is 36. For y, 4 divided by 2 is 2. Squared is 4. So this needs to be y squared plus 4y plus 4. Well, I added 4 in here times 25 is 100. So negative 36 plus 100 is 100. Now I divide out the 100. 4 and 100 cancel out to make 1 over 25. The x squared minus 6x plus 9 is x minus 3 squared. For the y's, the 25 and 100 cancel out to make 1 over 4. Y squared plus 4y plus 4 is y plus 2 squared. And the 100s divide out to make 1. So there it is. So we're going to do similar processes for the other conic sections over the next couple of classes. For right now, you do have a new homework. In my math lab that will be due for next week, Tuesday. There is no quiz due this Friday because of the test. Also, remember, if you wanted to do it for extra credit, the test to review in my math lab has to be finished by the end of the day today for extra credit. So you can still finish that up if you haven't quite done it yet. Also, remember, just like with test 1, you can do test corrections on test 2. We will have those due the Monday after Thanksgiving. That's the first Monday in December. So what is that? December 2nd. So that way you guys can have Thanksgiving break to finish those up if you need them. Anybody have any questions? Okay, well, you guys have a great day, and we will see you next week.